term. This term cannot be neglected if your system is rotating, plus the particle you are observing that is also moving with respect to the rotating frame. It cannot be neglected in that case. And in many practical cases, when we do motion on Earth, we have to actually consider this term. We have to consider this term really seriously. And the final one, usually for Earth, we can actually neglect this omega dot term because it's not accelerating, like it's not accelerating in the angular way. So we can neglect that, but it could arise. But point is, if this term exists, then it doesn't matter whether you have your like omega small or not, or you are moving or not. If you are looking at a point that is not at the origin, then you'll see this term always. But still, in practical cases, the most important term is this one. If you are looking on a system that's that is attached to Earth. Okay, so last time we talked about one important thing that we all noticed that there is a common feature between the non-inertial terms, that they are proportional to mass. Question is mass of what? What is m? What is this m represent? Mass of what?
The motion of a particle we are observing.
Yes, the mass of the particle we are observing.
Yeah.
So the mass of the particle we are observing. In textbook way, you can say it as a test particle, like you let on particle move freely on a field and see what happens. So that's your test particle mass. Okay, so m is the test particle mass. So whenever you have your f equals to 0, this, if there is a situation when you do not have any actual force in your system, then f equals to 0. And in that case, what will this guy see is ma equals to negative m va minus m omega cross r, negative 2m omega cross b, negative m omega dot cross r, right? In that cases,
yeah,
you do not have any external force applied on that, external real force applied on that test mass. Then the magic happens is that all the mass terms cancel out. Here you can cancel out these terms, right? Yeah. So you can see in non-inertial frame, when you do not have any applied force, the motion actually doesn't depend on the mass itself anymore. It's totally independent of mass. So whatever you're observing, a particle of 1 kilogram, 2 kilogram, or 10 kilogram, it doesn't matter.
Yeah,
right? Yeah, that's the important feature here. Because let me give you an example. So let's say you're on a frame that is actually a two-dimensional frame and rotating this way, and you're observing a particle that is sitting over there, right? So as you are rotating in this way, you'll always see from your reference frame that your particle is moving in this way, right?
Yeah.
And
no matter how much mass is.
Yes, it doesn't matter what the mass is. You'll always see the trajectory same as this one, right?
Yeah.
So last time we talked something about being like gravity being proportional to mass as well. So what's the specialty about that? That is, if your test particle is moving in a gravitational field, some gravitational field denoted as vector g, then the motion you observe, like F equal ma, on the other side, say you're seeing the same thing from a inertial frame. So these terms vanish, but you have your F, that is F is now represented by gravity, and that F equals to mg, right? Yeah. So again, the same thing happens, that your mass terms, they cancel out, and you're still left with a motion that is totally independent of mass again. So again, in gravitational field, it doesn't matter what the mass is, the motion will always be the same. So to us, it seems in a gravitational field or in a non-inertial frame, there is actually a defined trajectory for all the particles for a specific initial condition, right? As long as you have put your initial position and initial velocity, doesn't matter what the mass is, they will follow the same trajectory. So trajectory is kind of initially like already defined on the system. It's hardwired on the system.
But the source, I mean, which is pulling the gravitational force, it has some effect in the motion of the test particle.
So you're saying like G has a source.
Yeah.
You're right. Is like if there is a big M.
Yeah.
Over somewhere, and then in Newtonian's gravity we write it as negative G M divided by norm of the r minus r prime, where r prime is the position of that mass. Like that.
Yeah.
So what's the thing you were asking about?
If small m and capital M are comparable, in that case.
Okay. So yeah, I know what you're asking about. You're asking about if that test particle mass, small m, is going to change this gravitational field near to it or not, right?
Yeah.
So yeah, that's why we actually defined our test particle. There is a reason. We did it for something. Test particle, when we talk about it, actually its mass tends to 0. So we are talking about the limit case. So we are actually putting such a small mass that it doesn't affect its space-time itself, like the gravity itself. That's why we talk about test masses. Actually, we will see that we are in full glory. So now we have to discuss this. So yeah, is there any question regarding the last class, or do you have any new idea that you want to discuss? Hello.
No question right now.
Okay, right now you do not have any question. Okay, Jaber, remind me when it is exactly 9 o'clock at this time. So we'll have a break. Okay.
Okay.
Okay. Okay. Let's get started for today's class. So we'll start analyzing just one or two situations where there is non-inertial forces, like fictitious forces acting on the system, and we'll try to analyze it. So whenever we start with Newton's law, we try to discuss some simple systems that that can be analyzed mathematically pretty easily. So we are actually going to talk something about that kind of system, like a projectile motion. What happens if you release something, or what happens if you throw something in the air? What happens? So here we have two assumptions regarding the reference frame. So let's say this is our R. This is our R, and this is the axis of rotation. So it's rotating counterclockwise. and it's not angular velocity is not increasing over time. So omega is actually sufficiently small. Question is small to what? We'll analyze that. Okay, so let's start with this. So what happens when we throw something in the air? Say you're sitting latitude, like latitude is measured from the like what's this called, equatorial line, right? This lambda would be the latitude, right? This angle is measured from the equatorial plane, not the top point like we do in electromagnetism or mechanics. So yeah, you're sitting here and you throw something in the air and you want to analyze its motion. So how do you analyze it? So first you have to set up a coordinate system that's convenient to you. For our purpose, it's convenient to define our z direction this way, because then our gravity, that will be in z direction completely, and we consider that is our ex is this direction, like x direction is this, and the y direction is pointing inward to the plane, like at this point. You see the picture, like what I'm trying to express?
Yeah.
Let's redraw it. Let's redraw it. What I'm saying is like here is one equatorial line, not equatorial line, that's latitude line, like that. So one longitudinal line here, and then say you're at this point, and this is your z direction, this is your y direction, and this is your x direction. You see the picture, and say this is your origin, and like that. This angle is your lambda. You see what I'm trying to say? Yeah.
Yeah.
Okay, great. So now, if our omega is in this direction, so first thing we have to do, like we have to resolve our omega in this new coordinate system, right? So as you can see, EY, like we call it EY, and we call it EX, and we call it EZ. So as you can see, like omega is perpendicular to the EY always, right? This like tangent to this curve is going to be perpendicular to that one always. You see that?
Yeah.
So if you translate this one, so that this will be your omega here. So this angle is going to be 90 degrees. Now rest we have to resolve in other two parts. So let's see, our in our new coordinate system we need to write this omega x, omega y, and omega z. So omega y, it's fairly easy to see that we have this condition satisfied here. So this has to be 0. Now what about the other two things like omega x and omega z? Can you guys tell me? So what happens? What happens like if this lambda is over here? So then your z direction is like this way, right? And that's gonna be perpendicular to the omega as well. So when lambda is 0, the z component of omega has to be 0, right?
Yeah.
And in this case, so you can actually say, okay, it must be proportional to sine lambda, right? That, right? Like that. Hmm? And if your omega has a magnitude just omega without the bar, then omega z has to be this, right? Just to vector resolving, like it might be hard to see because of my bad drawing, but do you need a geometric analysis to see that, or okay, let's do a two-dimensional analysis. So I'm actually taking a cross section. Someone is trying to join. Okay, so I'm trying to draw a cross section like over this curve. So then our EZ would be, sorry. Our EZ would be this way and EX would be that way. And we are trying to resolve this omega into two parts of this. So omega is this way, and this angle that it creates from the equatorial plane, that is lambda, right? So then how do you resolve this thing? So as we can see, this line actually continuous one, like this line, and these two things are parallel, right? This line and that line is, those are parallel.
Yeah.
And how much is this angle?
90 minus lambda.
Pi by 2 minus lambda,
Yeah.
right?
Yeah.
So if this one is pi by 2 minus lambda, how much is that?
Also pi by 2 minus lambda.
This has to be also pi by 2 minus lambda, right? And if you draw a horizontal line over here, this angle should be your lambda, right? So if a vector creates an angle pi by 2 minus lambda with some another vector like the
Or by we can extend the y direction in a negative direction.
we need not to. So EZ dot omega, it must be proportional to omega number one, and then how much? Then it will be cosine of pi by 2 minus lambda, right?
That cancels sine lambda.
Yeah, so it becomes omega sine lambda. So that's what I have written. So if one part is omega sine lambda, that other part has to be omega cosine lambda, but we are not sure about the sine. So sine, you can see like this one is actually going in the opposite direction of omega, like not exactly opposite, but this thing is going to measure it in a negative way, right?
Yeah.
So
or cos pi by, or you can already write cos pi minus lambda, so minus.
yeah, that's true. Yeah. So we are on the same page, right? And like we could resolve our omega in our new coordinate system. I think everyone agrees at this part, right?
Yeah.
So do you guys have any question at this point, or we can proceed?
You can proceed.
Okay. So next thing, we have to resolve our velocity as well. So now we can actually draw a diagram at this point. So this is our z-axis, this is our y-axis, and this is our x-axis. So this is ex, this is ey, and this is ez. So say you're trying to throw something in air with some initial velocity v0, and after that things changes, like Earth rotates and it's affected by gravity. So this v0 is going to be changed, right? It's gonna get changed. So let's say at some arbitrary point, at some t time, the velocity is v, and we say that we can resolve our velocity like this: dx ex plus dy ey. Sorry, dy ey plus d is d easy, right? Okay, so that's going to be pretty generic. So next thing, what do we need to do? We need to do a order of magnitude calculation to calculate everything. So let's write down the non-vanishing terms for our for the motion in non-inertial frame. So ma should be equal to, first thing is f, right? So, we'll write down the expression of f later. So then we have negative m omega cross r, then negative twice m omega cross v. So we can neglect our omega dot terms like angular inertial term because it's not speeding up. The arc rotation is not speeding up. Also, we are not like moving at an acceleration with respect to some inertial frame. So we can neglect those two terms already. So now write down the formula for F. What's gonna be like, what's F? What's the actual force we are seeing here? Force or forces. So just lift it up, like physically. We throw something in the air and we are trying.
F equal to mg is it minus mg is it.
Okay, so you're confused about this, like the sign, right?
Minus
So,
mg is it, I think.
So gravitational force is actually defined as mass multiplied by the gravitational field. This field vector has this the direction inside of it only. So this is just that.
Okay, are we considering it as a function of position, or it's just a constant here?
Now we're considering it as a function of position, but if the initial velocity is not that high, then g is not going to get changed that much, right? So we can consider it's approximately constant. So when you throw a projectile, actually over its height g changes, but that small change, that minuscule change doesn't matter.
Yeah.
Right?
Yeah. We can include it.
So we can make an approximation here and write that. Also, we can make another approximation, is that we're almost in a vacuum situation because we're probably throwing really dense objects in the air. Okay, so let's consider vacuum. That's easy to deal with. Okay, next term is like m omega cross r, and then negative twice m omega cross d. So this term can be neglected as well because we have a big one. Mg is actually a really big, considering with respect to this one or that one as well. But the effect of this one actually like overweight this one. So we can actually neglect this one because it's proportional to omega squared, and omega is pretty small, so we can consider this as well. But we have to consider when actually we are on a really speedy system that's rotating really fast. So Earth is not rotating that fast, so we can actually neglect this term. And also, this thing actually it has a direction of negative of z here at this point. So actually we have to compare like with respect to g. So comparing with respect to g, this term is very small, so we can make like that as well. Like make it that. So then we're left with two terms only. One is mg and another is negative twice m omega cross b, right?
Yeah.
Okay, so at this point we can cancel out the mass. Actually, we could do it earlier. So our equation of motion finally, acceleration is equals to mg minus twice m omega cross b. So now we need the gravitational field g, and gravitational field, it acts in the negative, like in the downward direction in a local frame. So we can write g equals to negative mg EZ, right? So negative EZ is the direction and mg is the magnitude.
Shouldn't it be just G more M?
Sorry. Sorry. Yeah. Actually, yeah. Now it's correct.
Yeah.
Okay. So we can substitute that. So A equals to negative G EZ minus twice omega cos B. Question is, how do we handle this part? How do we deal with this part?
Wait, can you repeat the question?
So how do we deal with this part? How to handle this part?
We will. Okay.
Any idea?
And this is the velocity of the object, right?
Omega is the angular velocity of the
Earth, and v is the velocity of
There's
the.
no Y part.
Okay, yeah, omega doesn't have any y part. Yeah, that's a good thing actually.
Uh,
So only thing we can do actually, we take a cross product.
Yeah.
We cannot do anything else here. So let's do it. We have to do this at this stage. So ex, what's ex? Negative omega.
Cosine of lambda.
but by they are not actually constant vector.
Which one is not a constant vector?
Ex
Omega is a constant vector. That's not a problem.
but the unit vectors are not constant.
Oh, we are actually taking cross products in a local frame. Like you are doing everything here at this point, so it doesn't matter much.
Okay.
See, trying to do like you throw an object and it actually it lies somewhere else, like it falls somewhere else. So you're saying that actually it's changing the position, so its corresponding E should be changed, right? Like that.
Yeah.
Point, it's not moving that much. It's not moving that far that you need to consider that change of your basis as well.
Oh, okay. Okay.
It's like the same approximation we did with G. Okay, then you have this, and then your velocity is changing. So we do not know anything about it. So all we can write it as Vx, that is basically x dot, rate of change of x, and rate of change of y, and
Yeah.
okay, so we can do the cross product. What do we get? So Ex multiplied by this should be a negative term, y dot omega sine lambda. Is that correct? Then
Yeah.
y term is, we will have two terms actually. So one is x dot n plus sine lambda negative, and also there is a negative here, so it becomes positive. So omega cosine lambda and z dot.
Yeah.
And finally, Ez part is this negative omega cosine lambda and
Y dot. Yeah.
Do you agree with that? So
Yeah.
now we have to substitute it inside of that expression. So we substitute and get like A equals to negative G Ez negative twice and all these terms. So let's simplify it and write negative y dot omega sine lambda ex, then positive x dot omega sine lambda plus z dot omega cosine lambda dy, and then we have negative y dot omega sine lambda easy, right? Like that.
Yeah.
Yeah.
So for analysis purpose, we can actually neglect this component. Can you see it? Why? We can neglect this part.
Which part?
Since G is large
Yeah,
compared to it.
yeah. G is really large compared to this. So we need not to worry about that part, so we can neglect it. Approximately equals to 0. And what else? Can we neglect something else? I think not. We have to consider everything else now. So we are left with a. Okay. Also we can split our a. So like this, x double dot ex plus y double dot ey plus z double dot ez, right?
Yeah.
Yeah. So if we substitute, what we get? X double dot. What's that? Only this part.
2 y dot omega sine lambda.
Yeah. 2 y dot omega
Sine lambda.
sine lambda. And then y double dot, what's that?
X dot omega sine lambda plus z dot
X
omega
dot
cos
omega sine lambda
plus z dot omega cos lambda.
z dot omega cosine lambda.
There should be 2 in front of.
Yeah. There should be a negative to it, right? All these terms should be negative.
Yeah.
Is it right? Then we have. Actually, I should have cleaned up my whiteboard first. Okay, so what is z double dot?
Negative g.
Negative g. So this is our set of differential equations we need to solve, right? So which one would be?
I have a question.
Yeah, sure.
In the equation of A, why we considered the term associated with Ez equals to 0?
Oh, because this term, like you're considering, like
They are in the
yeah,
same
like
direction.
this term, right? Why are you considering this term to be 0?
Yes. Why we are considering?
Okay. If we wrote this, then this would be like this: plus twice y dot omega cosine lambda, right?
Yes.
And
So-
Z dominant.
So you have to consider like the magnitude of this part with respect to this part. This is already like in SI unit, it's 9.8. This is huge.
Oh, yes. The value of omega is very low, and that is why we have eliminated that term.
Yes. Omega is very small, so that's why you can actually consider like discard this term.
Okay. One more problem. As the background is white and the color of cursor is white, sometimes I get difficulty to find out the cursor. So, is it possible to change the color of the cursor?
Cursor means the pointer. Like I don't think so. All I can do is underline these things from now on.
Okay.
Let me check. Yep, I don't think there is a option over there. Yeah, I understand that's a bit difficult. Also, this pointer is really small, so sometimes it's hard for me to find where it is. Yeah, I understand your difficulty. Okay, guys,
I
are
think
you?
you can use black background instead.
No. That's bad for Ani. That's really bad for Ani. So are you guys still following? I think it's a little bit boring because it's a bunch of differential equation we need to solve. But what do? We need to solve it anyway. Okay, so let's do it. So the last one is pretty simple to solve, right? So if you solve it, what do we get? Z as a function of time, that would get you negative g divided by 2 actually. So half g t squared plus the initial value of that velocity, the velocity of that thing. So that is vz naught t plus the initial position, and we are considering initial position to be 0. So yeah, that's all. That's all we get, right? Yeah. So question is, what is our z dot? Because we need it here.
It's just minus GT plus VZ naught.
It's negative gt
Plus VZ naught.
plus bz naught. Okay, again, we are in a situation that this term, if you substitute over there, this is going to dominate again. Why? Because it has a g inside of it, and x dot is not going to be that big, right?
Yeah.
Because x dot doesn't have any other source, so we can actually simplify it to be like this. To be twice gt plus bz naught and omega cosine lambda. Do you see why?
But there is a problem with minus sign. So it will be GT minus VZ naught.
Yeah. Okay. Now it's correct.
Okay.
Okay, so this is our approximately y double dot. So how do we get our y from here? Y or y dot, like integrating one, just part one.
Here lambda is constant. Are you considering lambda constant? The latitude is constant.
Yes, obviously.
Okay, then it's simple integration.
Back of the arc, so lambda is pretty much constant.
Okay. Then it's easy to integrate, I think. Okay.
Then
Okay, I'm giving you the answer. Give me a moment.
so you're trying to integrate it, right?
Yeah.
There is only one p term. The rest are
So
constant.
let's integrate once, then we get we had gt that gives us like 2 half gt squared negative bz naught t omega cosine lambda. Then we have like y equals to 2 1/6 gt cubed negative half bz naught t squared cosine.
Yeah, but the initial condition.
Oh, the initial condition we missed that. Okay. So that should be plus by naught here, and also like plus by naught plus t, and
Times
we're considering
t.
like initial.
Why not? Plus why not?
No. We are considering like we have found things from the origin.
Okay.
Like, do you remember the diagram?
Okay, it's all right. Great, understand.
So you have flown from here. Okay. So then what? Then the last term, right?
Yeah.
So you need to substitute your y dot over there, and if you substitute your y dot, then what do you get? X double dot equals to twice 2 into half gt squared negative bz naught t omega cosine lambda plus by naught.
Why do you really need that? Because y dot is constant here. There is no acceleration at that direction. Y dot. Oh, okay. I understand. Yeah.
Includes the y dot. So x double dot
Yeah. Okay.
depends on y dot. So we need to write that. Is that correct? Yeah. So finally, you just integrate and find your x. So what do you get from integrating this one? It's again the same, similar kind of integration. See, it's just it has a quadratic term inside of it. So let's simplify it first. X double dot would be
We can ignore omega square terms like this.
Yeah, we can ignore the omega square part. So what are you left with? So actually this term, like this term, actually you can actually discard totally, right? You're left with only by naught omega sine lambda, right?
Yeah.
So then you have
2 by naught omega sine.
yeah, there should be 2. So x dot would be twice by naught omega sine lambda t plus bx naught. This is one thing, and then finally we have x equals to 2i. That 2 should be gone by this integration. So we can write by naught omega sine lambda t squared plus bx naught t. Is that okay?
Okay.
So what's our solution finally? So let's summarize. So our solution, the state is x equals to by naught omega sine lambda t squared plus dx naught t. Y equals to we need to simplify it a little bit, right? It's 1/3 gt cubed minus bz naught t squared, this thing multiplied by omega cosine lambda plus by naught t, and then finally we have our z coordinate, that is negative half gt squared, and then bz naught t. So this looks a little bit like complicated, but if you restrict our initial condition a little bit, then it will get simplified. So we are actually trying to analyze a motion. So let's say this is our z direction, this is our x direction, and y direction is pointing inside of it. So let's say so our particle in this xz plane. So this, then in that case, in that specific case, by naught, these things become 0, right?
Yeah.
So this thing simplifies to like this part is gone, this part is gone. So we are left with x equals to dx naught t, y equals to 1/3 gt cubed negative bz naught t squared multiplied by omega cosine lambda, and then finally c equals to negative half gt squared plus bz naught. So what's the difference between the projectile motion in non-inertial frame and this one? Like when we consider your art non-inertial,
Due to the y.
The y was 0.
yeah,
Y is 0.
previously had our y to be 0. That's the difference. Other than that, everything is same, right?
Yeah.
So you can see what happens actually. You have thrown your particle in xz plane, but your earth is rotating. So after a while, like it rotates in that direction. So this thing appears to be like out of the plane, right? So
Yeah.
let's draw the diagram from the top. So you have shown here, like you can see a point, like it goes like that and that, like in a plane. But the Earth rotates this way. So from the Earth's reference frame, you see that instead of going that way and coming that way, it just also move this way. So Earth rotates, and that actually gets deflected. So
Yeah.
what do you see from this origin? That's what I'm trying to explain. So let's say this is your xz plane, and this is your y. So actually, you assume that it would look like this, but instead of that, it looks like this. This is what happens because of the Earth's rotation. So to see that Earth is not flat and it's rotating, so you just need to throw something there really hard, and you'll see the result. So is it convincing enough?
Yeah.
Yeah.
Okay. Should we analyze another motion, or actually we're running out of time? That's the problem.
Yes, it's 9 p.m.
Yeah. Let's take a 10-minute break and come back.